spoke publicly about the World Trade Center, my brother objected pretty strongly. Now, my brother was in World Trade Center 6 on September 11th, and he had a lot of friends in 1 and 2, and he just said to me flat out, you can't talk about the World Trade Center. That's not something that we talk about. And I really thought about it for a while, and I said, you know what, maybe I shouldn't. But I've been speaking about it for a few years now. And I think that to not speak about the World Trade Center as a structural engineer would probably be equivalent to if my profession were in national security and I decided I should not speak about the World Trade Center. If I was in fire protection and I decided to not speak about the World Trade Center. Or if I was in air traffic control, to not speak about the World Trade Center. All of those things would be irresponsible. You know, if there's one thing that a structural engineer needs to do, it's such a simple, well-defined profession, it's to make sure that buildings stand up. And I think that, therefore, I say then that this is a most reverent presentation. In fact, what I'll principally be doing is beginning with the reverence towards this design. I mean, a lot of what I'm going to talk about is not the collapse, but the fact that this design itself was something that was exceptional in its own right, and then talk about the collapse, and then just a little bit talk about the future. Because all of these things are central to what a structural engineer worries about and has to prevent from happening, which is the collapse. So to begin with, it's a groundbreaking design from the 1960s. And in order to fully appreciate what was exceptional about the World Trade Center, you do need to take a course in High-Rise 101, the basics of high-rise design and how it is accomplished. And first, a few terms. So our building basics start with gravity. Now, gravity loads are applied to beams. The beams support the gravity load. Over here, I've got a beam sitting on a column and a column and a column. And the job of the beam is to support that gravity along its length and carry it to its ends. And then the column, in turn, takes these forces of gravity and carries them down to the foundation. That's how it works. What about 2 floors? So I begin with 1 floor, back that up. What difference does it make to the beam? Put yourself in the beam's shoes. If the beam, right now this beam's saying to itself, you know what, my job is to carry these gravity loads and carry them to the columns. One change is made. Now, those columns are sitting on top of other columns. Does the first beam even see a difference? Is there a difference for the beams? Or the beams pretty much the same? What would you say? Pretty much the same thing. The beam didn't even care. You know, all of a sudden, this column has another column underneath it. No big deal. Beams are beams are beams. Just beams. So the beams are all the same. On the other hand, what about the columns? Does it make a difference which column has greater load, this column or the column above? Which one has the greater load? Do you know? The one below, of course. You know what this reminds me of? This happens at my house, particularly on weekends, is I'm laying on the ground and then one child jumps on top of me. And then another child jumps on top of me, and then several other people on top of me, and I'm the guy on the bottom. The column on the bottom has to support the sum of everything above it. So if it's a 2-story building, it has to take, basically, beams don't care. The columns support twice as much load with twice as many floors. If we have 10 floors, then I think you got the pattern. In round numbers, how much more load does the base column have to take now? It's basically 10 times more. It's additive, 10 times more load. And so that if you were to consider the cost, because you have to pay for steel, the higher you go, how much more steel, how much more, this is really cost, how many more tons of steel do you need to buy as the number of stories goes from 0 to 80 or more? How does it vary, do you think? Like if I doubled the amount of floors, what do you think I would do in general to the amount of steel that I'd have to purchase? You, sir, what would you think? Double. Basically, pretty much double. You know, it's like a linear thing. It's pretty much varies linear, gravity steel. So yeah, okay, your building gets taller, you're paying more and more for every floor that you put on there due to the force of gravity. All right. There's beams and columns. That's like a computer model, but more real. There's a beam, there's a column. There's some iron workers who are putting the thing up. beams, columns. Okay, a little bit about stresses and stuff. So right now what I've got is a beam with a relatively short span, and it's got a load acting on it. When the spans are nice and small, then there's a little bit of deflection. I think you can probably see the amount of curvature that we've got down here. It's sagging a little bit. But what's pretty dramatic is if I take out that support and double the span, I don't really have enough height at this point. It turns out that the span's really important. It's not just important. The span has a tremendous impact on the level of stresses. So if I have short spans, I got nice, cheap, small beams. If I have long spans, there's my problem, and I can't just allow that problem to happen. I get big stresses. I require big beams in order to control the stresses that are acting on this thing. And it turns out that the dollars grow as the span is squared. The demand on the beam. If you double the span length, you've quadrupled the demand on that beam. That means 4 times more weight, 4 times more everything at this point. So this is important. Short spans are cheaper. Now, High Rise 101 was a book that was written in the 1930s, and it was the Empire State Building. This is a landmark building that remained landmark for a good 30 years, and it was the benchmark for how high rises are done. And it was based, to a great extent, on this fact: short spans are cheap. So when the Empire State Building was constructed, there it is, magnificent, cheap, simple, 1930s design. Here's its floor plan. Does anybody know? So here's a floor plan, the familiar look of Empire State Building, getting smaller as we move up, the setbacks moving inward. What are all these little black spots, do you reckon, on that floor plan? What are they? Those are the columns that are actually supporting the structure, and they happen to be pretty close. I mean, by modern standards. They're 30 feet apart because short spans are cheap. If you want to go to 60 feet apart, we just kind of did the math. Quadruple the money for all of the beams in all of the 86 rentable floors that the Empire State Building has. Short spans are cheap. Therefore, you get many interior columns. That's minimum cost. It's not popular with everyone, though. It's not popular with architects. It's mainly not popular with architects because of their clients. I mean, who's the client for this? The guy trying to rent it. That's who the client is. It's very, very, very difficult to rent a column. People will not pay good money to rent. These are not quite to scale. These columns are very large. They occupy a pretty important amount of valuable, rentable Manhattan real estate. So this is the Empire State Building today. If you gut a floor, this is what you're looking at. An amazing size of the column. Sometimes I like going into the restaurant. There's a Blimpies in the basement of the Empire State Building. And you go there and have a table next to a column. Because the column is something you can't even wrap your arms around. It's an enormous column because of this effect of 102 total floors and all of their load add up so that at the bottom the column is enormous and very closely spaced. So this is actually somewhere in the middle. That's very close, very large columns. And as a consequence, narrow hallways, small offices, generally a very inflexible kind of layout. If it weren't for the fact that the Empire State Building is a landmark, they wouldn't be able to rent it. They would have a very hard time renting that kind of space today. But it's a landmark. I'd love to have an address in the Empire State Building. So they are able to rent it. But next topic. So that was topic number 1. High Rise 101, it has to resist gravity loads. A few facts come from that. The columns get bigger and bigger as we go down. And we try to make the spans short because that makes things cheap. The lateral system, this is the system of members that exist to resist things like the wind, the earthquake, anything else? Wind, earthquake, those are the biggies right there. So I have a low-rise building here. Here's a low-rise building, and here's my low-rise balsa building. I apply some forces to it, and then I decide to make my building twice as tall. So we did a little bit of pseudo-mathematics a few minutes ago with gravity. What happens when I made a 1-story building a 2-story building? What happens if I double the height of this building? What would you say would happen to the magnitude of forces acting on this thing? It's wind, by the way. There's a wind pressure, you know, and so if I go with twice as much building, what would you say the effect would be? What kind of increase would there be with number of floors? Pretty much, yeah, double the height. You're going to double those forces. And it's a linear thing, you know, so you go 10 times more height, 10 times more forces, but there is something more to it. Let's see. Now this building is kind of low. I can move it with a gentle breath. I can move this. Let me put it up where others can see it a little bit better. Get rid of my beam. Okay. A little bit of force being applied, a little bit of wind is applied, and I decide that the building should become taller. Do I have enough overhead here? Yeah, I think so. So, add more. Let's do it this way. Pardon me a moment. As I turn my vac on everyone. That's good. All right, twice as much building. Yeah, now I need to actually put this lower. Yes, my binder clip building, my cocked binder clip building. I will actually put it lower. You know why? Because I need to blow on this thing. So you make it twice as high, the forces become twice as high, but something else also grows. See, when it was low, there was wind down here blowing on it. Now there's wind up here and here, with a lot more leverage. The difference is not the magnitude. The magnitude of force just doubled. But the other thing that happened, building gets taller, leverage. More height means more leverage. Now, what are your common examples where you describe leverage to someone? What are you usually grasping in your hands? And you say, well, this is what leverage means. What would it be? Like a wrench. Exactly. It's basically the building is just one big wrench at this point. Now you got forces that are getting bigger and bigger, but then all the distances are also growing. So you have two effects that tend to increase as the height increases. So what happens with wind is stresses increase with the building height squared because of two effects, not one. Double the forces, also double the height. And so that is why with a lateral system, let's see, your gravity steel, we already established, just growing linearly. And then your wind steel just goes to the roof. Your whole building is doing everything it can just to resist the wind. There are real limits to how tall you can go because of how drastically this parabolic thing is going up. So the costs start to really rise rapidly. And the challenge is lateral. That is the challenge. You know, right after the collapse of the World Trade Towers, there were, I don't know what's the proper politically correct term, nitwits in the media who would say, let's design a building that's weightless and 2,000 feet tall. Hold on. Even if there are no people in it, I think what we've already established here is that it doesn't really matter if you've put people in your 150-story building or not. A 150-story building is just trying to stand up in the wind. People or not, doesn't really make much difference. So, frankly, the World Trade Center was already as light and weightless as it's going to get. I'm going to argue here it was an exceptionally cost-efficient design that you're very unlikely to ever be able to beat because of this battle. The challenge is lateral. One way you can battle it is with the sort of frame I've got here. This is a rigid frame. What we have in a rigid frame is, well, what do we not have in a rigid frame? What we do not have in a rigid frame is we do not have braces, diagonal members in here, truss members. There are none of those things throughout the frame. The frame is standing up due to the simple fact that the column is connected to the beam with something that can resist bending. This little connector that I've got, well, that's a little connector. How about, what would it really look like? Well, this is a little connector. This little connector. This would be an example of a bending resistant connection. There's the beam, there's the column. If I go and bend the beam, I am surely also bending the column. That's why that frame is standing up. If that frame did not have connections that are able to do that, if instead I had this, okay, this would be, can I try to stand it up? Okay, this would be an example of it's not resisting bending. I made that out of tape. So two members held together with tape. Well, they'll hold forces. They'll hold forces, but they won't hold any bending. So this is a case of it works because those connections are there. That's why this thing stands up. Bending, though, is a very inefficient thing. I think I illustrated the inefficiency of bending. And if you don't remember, this is the inefficiency of bending. that flexibility, that really astounding flexibility. Let's see. I could probably put about maybe 1/10 of a Newton meter on this thing and just break it. On the other hand, if we were to pull on it really carefully, I mean, and only pull on it in tension, without putting any bending on it, we might be surprised by being able to put, oh, I don't know, no, let's not break this or anything. You know, if I were to put, what is this? This is like a gram. You know, let's put a gram of bending, and then let's put, we're probably pulling a 10 or 15 pounds at this point. Can we break it? I'm sure we could. Let's not though. It might, we could, no, we will not. The point is that bending is a very inefficient way to do anything. And as a consequence, what is inefficient? Do you really care what inefficient means? It's expensive. If you're trying to resist the loads in this 100-story building using bending, it's going to cost you an awful lot. This illustrates the bending a little bit, I suppose. So here is it's a distorted view of a building. It's a computer model, of course. How do I know it's bending? Well, look at that distortion. Do you see that S shape that happens? The building racks back and forth. Let's see it again. The building racks, and the beams are just doing this, back and forth. Everybody see the S's back and forth? And I kind of established how flexible and weak this thing is in bending. If I could devise a force system that didn't rely on bending, it would be an awful lot more efficient, aka cheap. There are advantages, though. Well, yeah, okay. So the disadvantage, you may require huge beams if this building gets tall. That's unavoidable. The beams might become monumental as the building gets taller. There is an advantage, though. You know, architect, developer, people who want to rent space are at least happy that there are not a bunch of diagonal members cutting through people's offices. At least that doesn't exist. So that's an advantage. If you're trying to rent this, which is what we're really trying to do, that's a good thing. The alternative is a simple brace frame. That little dot is intended to represent this little dot. So this is a connection between a beam and a column that does not resist bending at all. It's the same. It's equivalent to this. Now, if I assemble a bunch of pin-connected things like this, I'll get it up, and then it would just collapse because I would need to have triangles in here. I would need to have trusses at that point to make the thing stable. So you can brace up like where all the elevators and bathrooms and stuff are, in the middle of the building. That is a way to make a building stand up to lateral loads. They resist no bending. You know what? Bending is a good thing. You know, we demonstrated that. If you eliminate bending and then just rely on these members in pulling or in pushing, in tension or in compression, it's far more efficient. So that if you apply a lateral wind force to this, it pushes, and it grabs this member and it pulls that member. Pulling that member has been demonstrated to be a lot more efficient. We can kind of see it when we, what does it look like? Well, okay, granted. Now, okay, I've made this computer model, so I can make the distortion whatever level I want. But the level of back and forth movement is less. What you also see is that this beam is just going back and forth without any bending because it's connected by pins at the end. So it's just going back and forth. The only job that beam will have to take is just the gravity. That huge amount of wind that's been a problem won't be a problem for these beams because they're not participating in any bending from the wind. And on the other hand is if I start to get 100 stories tall, I might have to inform the architect that everywhere I can, I've had to put braces and there's no other alternative. It's rentable. It may consume a lot of space. So what was the World Trade Center? Well, the World Trade Center was not your normal building. The exterior columns were 3'4" apart. 3'4"? That's how far apart these columns were. And then they were rigidly connected with a bending resistant connection to the beams that were extremely deep. I mean, really relatively very deep. I mean, these little windows were just like little punch outs in what was otherwise a tube. The whole building was basically, it's a kind of rigid frame. What was it? Was it braced? Was it a braced frame? Was it a rigid frame? It was a kind of rigid frame, but normally you have columns in a building that are like 30 feet apart. Here, they're 10 feet apart. Did I mention? I didn't mention it. That when you have a bending member, that if you cut its span in half, you change its deflection by a factor of the span to the third power. So if you cut what was a 30-foot span down to a 3-foot span, and I don't know if I can do that kind of math, I have to take 10 to the third power. You've made it 1,000 times less bending. Because yeah, it's a beam. All right, great, okay, sure, fine. It is a beam, but it's an extremely short beam. These things are so close together that the bending deformation is very small. And you know what you've done? You've taken the entire building and just made it into one big tube. What's the benefit of a tube? Okay, I don't lie real often, only for academic purposes. And this is not a lie. The amount of steel which is contained in that cross-section is the same amount of steel, this is deceptive, as in this cross-section. This is a hollow tube. This is a flat piece of steel. Now what's happened? Manufacturing-wise, they've taken a material like this, rolled it really, really flat, folded it 5 times, and then welded it back together. Let's see. All right. I can't possibly bend this thing. You want to have a crack at that? See what you can do with that. On the other hand, you know, the amount of bending stiffness you get when you put something into a proper shape, and the proper shape is nothing more than put all the material for the building on the outside. Like, what was the World Trade Center? A few hundred feet along its length? So you've got a tube. That's a 1-inch tube. The World Trade Center was a several hundred-foot tube. And that shape is what made the World Trade Center fairly brilliant. So what happened from this, sorry about the filth, that does happen with steel. It is kind of filthy. There's no interior bracing. Yet there's no beam bending. So the beams when you put the wind on it, the beams are just going back and forth like this. Okay, that means the beams, all they have to do is support gravity. They don't have to support the wind. The wind was a big, hairy problem. It's no longer a problem for the beams. That means the beams can be really small. So small that the World Trade Center is one of the few examples I can think of they used bar joists. It's a 114-story Walmart. There aren't very many 114-story Walmarts. It's possible because of the fact that the beams only have to carry gravity. They don't have to take this major wind problem at all. They are completely removed from that system. So you can use the lightest thing available, because you can, and it's a bar joist with a span of 60 feet. 60 feet's big. So it's twice as long as the spans of the Empire State Building. It's real rentable. It's all that good stuff. If you look at the floor plan, granted, I will grant you that an awful lot of area is taken up by this. Anyone know what all these boxes are? What are those things? Do you know what those are? There's a lot of boxes on the ground floor to every high-rise building in order to get up. That's all the elevators. You know, another thing that I don't talk about because I'm a structural engineer is that one of the limits to how high you can go is the higher you go, the more elevators you need. The more elevators you need, the shocking amount of real estate is occupied by elevators. This is real. I didn't even make this up or anything. All that yellow stuff is unrentable core. It consists of bathrooms, sure. It consists of bathrooms, mechanical, electrical, elevators, etc. This is your rentable space. But I will say that rentable span is over 60 feet. So there are the bar joists. The bar joists simply span from the core. Imagine like a pillar in the center of the building to the outside. That's all they have to do. And okay, so a little bit now about connections. How these connections were done. Okay, a simple connection is a term for what I've demonstrated, I guess, a few times now. This is a simple connection. This connection can resist forces. It can resist any forces we need it to take, but it does not resist any bending. As opposed to this one that I had, well, this one, that connection does resist the bending. Okay, so it resists the forces, but it's free to rotate. There are basically, in our world, there are 2 kinds of simple connections that are used in most buildings. Okay, one is something like this. Now this is a simple connection. I know it doesn't look like a pin. It doesn't look like a pin quite the way this looks like a pin. This is clearly, just a bolt in a hole, free to rotate. This one is also like a bolt in a hole, free to rotate, merely because the connection is only towards the center of the entire section. The real meat of the section is on the outsides. That's why it's an I shape, because the meat has been put to the extreme, but that extreme is not being connected. The part that's connected is just this thing. So it's free to rotate. That's one possibility. Okay, so we bring our bolts in. There we go. Now the next one is a seated connection. A seated connection is I take a seat, like this one, and I'm not entirely ready for it. Let's see, I get my seat on there. Getting closer. Good. Okay, I clamp a seat in place. Something for a beam to sit on. A beam like this one. Now, the way this first one went up, by the way, it was lifted high in the air. And then there was an iron worker who's perched up a few hundred feet in the air, attached to this column, clinging on the column, sitting on the column somehow. And then the iron worker matched up these holes to, let's say, those holes, or those holes. Put 8 bolts in place. 8 bolts. Put 8 bolts in place, and there it is. The other one, on the other hand, that seat was already there. Can everybody see the seat? Okay. That seat was already there. It was welded to the column, and the beam flies through the air, and the iron worker perches up there and lands it there. And frankly, it's done. Now, he'll put a ceremonial little bolt in there. I say ceremonial because he does need to make sure that at least between now and a few weeks from now, it doesn't accidentally slip off. But once the building has had concrete slabs and stuff on there, it's pretty much just sitting on it, just plopped on there. I'll put a ceremonial bolt there just to keep it there. That's it. Okay. So you have the seated connection. Beam comes in, pretty much done. That's it. Put an angle on top of it just for looks. All right, so in our world, in American structural steel, those are the 2 most common types of connections that we have. A simple frame and a seated connection. They both do what they're supposed to do. What are they supposed to do? Well, the main thing that they're supposed to do is take vertical forces from remember all that gravity? Right, the beam's going along, there's gravity, there's people, there's furniture, there's stuff on there. Carry that load to the column and then put that load on the column. That's what it's supposed to do. That's pretty much all it's supposed to do. And both of them do that. You put a load on it, it'll do it. And they do so without resisting any bending, so they're free to rotate. I know they look heavy, structural steel, but they're free to rotate just like this. And they're both widely used. World Trade Center happened to use the one on your left, a seated connection, for the bar joists. So here's the details these details were done in the 1960s. There's the exterior wall, and there's a seat. Here's the interior wall, and there's a seat to a column. We have another one. Yep, right there is a little seat angle. And then there's one more. There's a channel, and then there's a seat right here. And then I would also say, and this is mainly for the benefit of the gentlemen in the back who know a little bit about structures, is that this building is enormous. The spans are enormous. The only thing holding it in terms of bolts are 2 5/8" bolts, which are just about the smallest bolts you could possibly use in a building. Because they're not there for any structural purpose. They're there to just hold it until next week when the slab gets poured on this thing, and then it's not moving anywhere. Because remember, vertical forces come down. This thing just has to carry those vertical forces to the column. So the bolts are just there for a few days maybe. There's the seat. So this is construction circa, 1972 or so. There's the seat. Oh man, this was efficient. The exterior wall, there's the exterior wall of this thing, all prefabricated columns, massive plate girders on the outside, and there's the seats. and then these, they're almost like a 60-foot long prefabricated bridge. They get landed on top of these seats in these prefabricated sections. That was kind of a little bit of foreboding because of the September 11th collapse. To begin with, okay, so this is a computer model that was done by people who are working for FEMA, showing the impact. And one of the first questions that researchers wanted to determine was if we were to analyze this and know the fact that these columns are completely missing, because they were, what was the effect on the structure? I think a lot of people in the public wanted to know, would it have fallen down for structural reasons alone? Is that enough to bring it down? Now looking at, right here on the left are how the loads are supposed to make it to the ground. You know, so I add more stories. As I add more stories, all of that load has to make it down to the ground. So if there's a load up here, that load comes to this column and it just travels and travels and travels and travels and goes all the way to the ground. All of these loads have to eventually make it through all of these columns to the ground. Now when I put a hole in there, on the outside the forces still make it down the column and make it to the ground. What exactly happens to a load right above the hole? Load is coming down, and load, and there's nowhere to go. Yet it's standing. What's happening here, like if I'm a column right there, I am not standing on a column below at all. I'm actually reaching up to a column above and hanging from it. That's what's happening to all of these columns. All of these columns would normally be standing on firm ground with a column underneath. They're not. They're reaching up to a column above to hold them up. And they're actually kind of arching over the gap. You know, it's like the center of this building has to span this hole with an enormous weight on it and then transfer it somehow to the outside. And then the question is, can I, with all of that weight on top of me, carry it to the columns on the outside, and then can those columns in turn support all of that extra load? What you have to understand is that these columns that are right outside the hole were already designed to be adequate, to be safe, but now they're taking a huge chunk of extra. All of that extra has to make it over to here, arching like I was just arching over the desks to get to that spot and to get to this spot. So we analyze it. We drum roll. Anybody play the drums? Yeah, there's a factor of safety, that's what that is, of 1, meaning that based on the computer model, it was safe with no additional safety. It would not have collapsed for structural reasons alone, despite that gaping hole. And by the way, that is a gaping hole to put in a building. Despite the gaping hole, it's able to span to the outside, put extra loads. What is this? This is the hole, by the way. That's what this is. Here's the hole. So there are no columns. It's dumping additional load to the next adjacent columns. And this graph is now giving you how much safety is there. Any number that is greater than 1 would mean, in this case, ratio of demand to, what the heck does that mean? Anything greater than 1 would be unsafe. So these are all very safe, decent, scary, very, very scary, but safe. It would not have collapsed for structural reasons alone. Okay, so now I had foreboding a little bit earlier. So why was I talking about connections? Because it has a fair amount to do with the collapse. Okay, so revisiting a simple connection. Its job is to do that. Its job, this red arrow is indicating all of the force that is driving down, you know, maybe 50, 60, 100,000, no, probably more like 120,000 pounds or so is what's coming down in a typical World Trade Center connection. Right there, 120,000 down, and then equal and opposite, you know, like Newton's laws and stuff, opposite going up. It works. Oh, this one works too. Nice thick plate. It'll work. It's been analyzed by competent engineers. They both do the primary thing they're supposed to do, which is that. Take those forces. They also do what we kind of understood they would do. They freely rotate. They rotate, not as extreme as this, but they do rotate, and we understand that that's what they're supposed to do. There is now one difference. If I apply tension to this thing, that would mean, well, how would that happen? See, all right, if I'm a designer, certainly in 1965, and someone were to ask me about tension, I would say, What tension are you talking about? What force is taking this and pulling it this way? We understand there's gravity shoving it this way, but there's nothing pulling it this way. So why even go into this debate about the fact that this one, by the way, has a bunch of bolts. Mine has more. Mine happens to have 4 on both sides. And they're big bolts. It'll take that force. On the other hand, did I mention that this one, that seated connection, doesn't, for all intents and purposes, has no bolts here. It's just sitting on a seat. So if you go and pull on it, it's just going to head out. It just does not resist those forces at all. But again, you know, it's 1965. I'm thinking, I'm a designer for this building. I never actually would have thought about that. There are no forces. What am I worried about? Well, fire is the issue. So here's what starts to happen when we get high temperatures on steel. It becomes a lot less stiff. The steel starts to stretch considerably. The first effect it has, before I get into those connections, is buckling. Buckling is what happens to a column when it's a long, slender column. Pardon me while I get my apparatus together. I need this. Long, slender column. Here's a long, slender column. Pardon me as I put this in. Okay, so I'm going to assess how much force this column can take before it buckles. And buckling would be that. And it can't take any more. And in other words, what's the most it can take? That's all it really means. Okay, and I'm using, these aren't American units. They're also not metric. This is the nut. It's not a Newton. It's not a pound. We're going to put one nut. Oh. One nut, 2, 3, 4, 5, 6, 7, 8, 9. Can I do more? It's toast. Okay, 9 is the number. Now, what I would like is if you could, I would need you to be a brace. Now what a brace is, what I need you to do is just kind of take your fingers, you might have to stand up, take your fingers and just hold it right down the center without really touching it. See, I'm just barely touching it. Okay, if you can do that. Now, I'm going to see how much additional I can put in there. Because you know how with beams, being long was bad. It wasn't just bad, it was bad squared. You know, you double it, double the length, and it gets 4 times worse. Okay, how about a column? It has 9 nuts in there. There's 10. And if you just move just slightly this way, there you go. Does it look pretty straight to everyone? Reasonably? Okay. 10, 11, 12, 13, 14. And she's not touching it or anything. She's just gently. Yeah, just come a little closer this way. Good, good. 12, 13, 14, 15, 16, 17, 18, 19, 20. Is this ever going to end? 21, 22, 23. Pardon me. 24, 25, 26, 27, 28. And I cut to the chase. Eventually, if you can just continue to be the brace, it forms that shape. And you're just barely touching it, right? Just barely. She's not doing anything. She's just barely touching it. Just touching it enough to increase how much it can take by a factor of 4. It would have been to 36, but I'm full. Okay, thanks. So it's really important for a column to be short. Now, all right, clearly I must be wrong with my slides or something. What does short have to do with this? I'll hold that thought for a second. Okay, getting back to the column then. The column has a seated connection. I'm actually going to remove this beam and just look at the seat. And I've established that if this was a different kind of connection, I would be able to pull on this and hold that column in position. But it's a seated connection, so it's just going to slide right off if I do attempt to pull it all. All right, that's established. So there's this huge stretching of beams that happens of fire. The temperatures are upwards in the 12 and 1300 Fahrenheit range. And I look for a moment at a different building. This is not World Trade Centers 1 and 2. This is number 5. Has a connection that is a simple shear connection. It's not a seat. It's got a cluster of bolts on there. And under huge fire, it drapes like a clothesline and doesn't fail. And I've been into buildings after massive fires. What was the name of that building? Anybody from Philadelphia? No Philadelphia people? Anybody know the name of that hulking 30-story building that sat there for about 2.5 decades after a fire? No? I was in this building. Is it Mellon Bank? No, Meridian? Some bank. Okay, you get out of the elevator and you start walking. And you walk, and then you suddenly find that you're walking like this, because the beams that were 13 feet apart are now 4 feet apart, and you're crawling. Okay, because of that massive fire, the beams turned into clotheslines. Now, if you had a connection that could support a clothesline, do I have a clothesline? I have a clothesline. So if I had a connection that could support a clothesline, that would be like this one. Okay, put it in there, and clamp it in place. Now it can drape, and I'll pull on it, and it won't come loose. I can put loads on this thing, and it won't come loose. And it will do what this building did, which was it deformed an awful lot, but they never pulled out. You just have a series of clotheslines. They, by the way, you know that tension I told you that I didn't care about it because it was 1965 when I designed this building, it didn't matter because there is tension when you form a clothesline. Now there is. There's enough tension, I'll pull the column over. Okay? And that's the second part of it. Part 1 is World Trade Center 1 and 2 did not have that capability. Other World Trade Center buildings did. And many others do. The second one is more subtle. Just as this slab pulls off because it wanted to be a clothesline but couldn't be a clothesline because there was no way of holding that tension, it fell. When it fell, can anybody see what happened to the length of the column? How long was the column before? Before, the column was this long. Now the column is this long because this slab has dropped out. And we just demonstrated that being twice as long is 4 times worse for the column. If that column was in trouble, so we established 10 minutes ago that there are columns in this building that were in trouble. They were already at 100% of what they could take. They're cool, they're all right, no fire, we're fine. They're at 100%. They can't take any more, but if you double how long they are, they're in serious trouble. So the slab pulls out. Oh, by the way, it's also a moving dynamic body, so it's impacting the next slab. That slab was probably also in trouble. So there are several effects at the same time. Most notably, the column's longer, and there's a moving dynamic force that's suddenly happening. And at that point, I'm afraid it's done. There's nothing else to say. That is the role of cable action, or the lack of role of cable action in the World Trade Center towers. I don't suppose there's any structural engineers in the room, are there? And I just say that because one of the things that or architects, I by no means mean to give you the exhaustive explanation of everything there is to know about the World Trade Center. No. I'm pretty much isolating a few interesting issues from design to collapse and now to the future that I feel an audience can understand. So if there was a structural engineer in the room, I'd say, hey, calm down. I know there's many other issues. We don't need to get into those other issues. These are just a few. And it leads to the future. The conclusions. There are a few. First of all, I started off by saying I am lavishing praise on this building. You know, there's no irreverence here. There's reverence. I knew people in World Trade Center 1 and 2. So there's reverence for them, and there's reverence for the building. The building was actually extraordinary. That tube lateral system is just an amazing system. It's going to be very difficult for any building to be as efficient as that, because first you're going to have to convince an architect to live with windows that are that wide. If you can convince an architect to live with windows that are that wide, then we'll be able to approach that kind of cost effectiveness and efficiency. And it could. The World Trade Center, there's no question, this is probably common public knowledge, but it could have survived. Loss of columns. Very high redundancy means that there are so many columns you could afford to lose quite a few. And that's a good aspect for this building. With having that many, you could lose quite a few and survive it. The fire softened the beams and they softened the columns. The beams want to become cables, but because of that seated connection, they can't become cables. If there was cable action, then the building is a lot more survivable. I'm not going to go out on a limb and say that building stands with cable action. That's probably still not the case. There's enough other circumstances the building probably still falls. Probably stands a lot longer if you've got a connection that can take that cable action. And I think that's it.